Several students titrate 25 centimeters cubed of the same solution of sodium hydroxide, NaOH aqueous, with hydrochloric acid, HCl aqueous. One student obtains a smaller titer than the other students. Which procedure explains the smaller titer? A. The burette readings are taken from the top of the meniscus instead of the bottom of the meniscus. B. The conical flask is rinsed with water before carrying out the titration. C. An air bubble is released from the jet of the burette during the titration. D. The pipette is rinsed with water before filling with NaOH. So if we talk through our options, firstly looking at A, if you're consistently reading from the top of the meniscus each time, this isn't going to affect the overall titer. It's just going to have no change because you'll still be having the same difference, but the numbers of each bit will be different, but the actual titer won't change. So just as a recap, when water's in a pipette or a burette, it will have a slight curve and the meniscus is the bottom of the curve, and that's where you should read your volumes from. Then looking at B, so if you rinse a conical flask with water before carrying out the titration, this is also going to have no change, and that's because you're still going to have the same volume in the same moles of sodium hydroxide. You're just going to have it in a slightly rinsed conical flask, and because sodium hydroxide and hydrochloric acid are going to react on a mole by mole basis, then it's not going to change the titer because you're going to have the same moles. Whereas if we look at D, when you rinse with water before filling with NaOH, that's actually diluting the number of moles of NaOH there are. So this means that less HCl is needed, therefore you've got a lower titer. So the answer is D, but if we just look at C to get completion, if you have an air bubble released from your burette during the titration, this is going to mean that your titer is going to be bigger, because as you're getting the same gap, if you've got a big air bubble that's released, you're going to still keep adding more acid because you still need to neutralize the sodium hydroxide, but part of your volume would have been this huge air bubble, which is going to mean that your titer is going to be bigger. So this results in a higher titer. So the answer for this question is D. And to get the mark for this question, you need to write D in the answer box provided. Which statement gives the numerical value of the Avogadro constant? A. The number of moles in 12 grams of carbon, 12. B. The number of electrons lost by 20.05 grams of calcium when it reacts with oxygen. C. The number of molecules in 16.0 grams of oxygen. D. The number of atoms in 1 mole of chlorine molecules. So let's start this question by identifying Avogadro's constant. So Avogadro's constant is 6.023 times 10 to the 23. So if we look at the different options, looking at A first, we're going to use the equation triangle of mass divided by relative formula mass times moles to work out the number of moles in 12 grams of carbon-12. So we do 12 divided by 12, which equals 1 mole, which is not Avogadro's constant, so the answer is not A. Next, looking at B. So this question requires a little bit more calculation. So again, using the equation triangle to work out moles, we've got 20.05 grams of calcium, and we're dividing it by its relative formula mass of 40, and that equals 0.5 moles. And this is equivalent to the loss of 1 electron. But when we form calcium oxide, we lose 2 electrons. So we're going to multiply this by 2, so 0.5 times 2 is equal to 1 mole. But this question isn't asking about moles, it's asking about the number of electrons lost. So to work this out, we multiply the number of moles times Avogadro's constant, and as we're multiplying by 1, we're going to get Avogadro's constant. So this means our answer is going to be B. But with multiple choice, we need to check all of the options to make sure that this is correct. So looking at C next, so we're again using the equation triangle. We're going to do 16 divided by 16 times 2 because oxygen naturally occurs as O2. So dividing this by 32, we end up getting 0.5 moles. And we want molecules, the number of molecules in this question, so we need to multiply by Avogadro's constant. So 0.5 multiplied by 6.023 times 10 to the 23 is equal to 3.01 times 10 to the 23. And this is not Avogadro's constant, so it's not C. Finally, looking at D, the number of atoms in 1 mole of chlorine molecules. So in chlorine, we're going to have Cl2. So we're going to have 2 mole equivalents. So we're going to do 2 times Avogadro's constant, which again is not going to equal Avogadro's constant. It's going to equal 1.204 times 10 to the 24, which is not the answer we're looking for, so it can't be D. Therefore, our answer is definitely B, so we can write this in the answer box provided, and to get the mark for this question, you need to write B in the answer box provided. 0.80 grams of element X is reacted with 0.40 grams of O2 to form an oxide with the formula X2O3. What is the identity of element X? A. Aluminium, B. Titanium, C. Germanium, or D. Molybdenum? So firstly, looking at this question, we can work out the charge that X would need to have. So as O3 has a 2 minus charge, that means that it's got a 6 minus, and then we've got X2, so we'd need positive 6 to counteract this 6 minus. Dividing this by 2, we get plus 3. So that's the charge that element X would need to have in this formula. But that doesn't help us a massive amount with this identity question. So instead we need to try and create a balanced equation and work out moles and relative formula masses. So if we have X plus O2, that's going to produce X2O3. Balancing this equation, we would need 3 O2s, 2 X2O3s, and 4 X's to make this a balanced equation. Then we're going to use the equation triangle of mass divided by relative formula mass times by moles. And we're going to work out the moles in this question. So using the data we've been given about oxygen, we can do 0.4 divided by 16 times 2, and that equals 0.0125 moles. Then we can use the molar ratio to work out the moles of X. So that would be 0.0125 divided by 3 and multiplied by 4. And that equals 0.017 moles of X. So now we can use this equation triangle to work out the relative formula mass of element X using the mass we're given in the question. So we can do 0.8 divided by 0.017, and that equals 48, which is the relative atomic mass of titanium. So that's our answer for this question, and we can write B. So to get the mark for this question, you need to write B in the answer box provided. Phosphoric acid is a tribasic acid. What is the mass of CaOH2 that completely neutralizes 100 centimeters cubed of 0.1 moles per decimeter cubed phosphoric acid? A, 0.49 grams, B, 0.74 grams, C, 1.11 grams, or D, 2.22 grams. Firstly, in this question, the key piece of information to take note of is that phosphoric acid is tribasic, which means it needs 3 base groups to neutralize it. And we've got calcium hydroxide with this OH2, so it's got 2 base groups attached to it. And we have 100 centimeters cubed of 0.1 moles per decimeter cubed of phosphoric acid. So we're going to use the equation triangle first of NV times C, which is number of moles is equal to volume times concentration, which we can work out using the information in the question. We can work out number of moles by doing 100 times 10 to the negative 3. That's converting centimeters cubed into decimeters cubed, and then multiplying by 0.1, which gives us 0.01 moles. Next, we need to work out the relative formula mass of calcium hydroxide, which is going to be 40 plus 16 plus 1 times 2. And this equals 74. This is because we're going to use a second equation triangle to work out mass. We're doing mass is equal to the number of moles times the relative formula mass. So in order to work out the number of moles, it's not the moles we've calculated. We need to manipulate it using the data in the question. So firstly, what we need to do is 0.01 divided by 2. And then we need to multiply it by 3. Doing this means that we're calculating the correct amount of calcium hydroxide. Because we've got these 2 OH groups, that's why we divide it by 2. And we multiply by 3 because it's tribasic, so we do need 3 OH groups overall. And this equals 0.015 moles. So then we're going to do 0.015 times 74, which equals 1.11 grams. So that equation is just using the second equation triangle that I've written. And 1.11 grams matches the answer for C. So we can write this in the answer box. To get the mark for this question, you must write C in the answer box provided. Which statement about elements in the D block of period 4 of the periodic table is correct? A. Chromium atoms have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. B. Copper plus ions contain an incomplete 3d subshell. C. Iron 2 plus ions contain 3 unpaired electrons. D. Scandium forms ions with different oxidation states. So let's look at these individually first. Looking at A, chromium atoms have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. This statement is correct, and it's based on Hund's rule, which means that electrons want to fill up singularly before they pair up. So it's going to be more stable to have individually filled D subshells and one individually filled 4s subshell than it would be to pair this 4s electron with one of the 3d electrons. So this statement is true. Then looking at B, copper plus ions contain an incomplete 3d subshell. So if we do the electron configuration of copper first, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s1. 1. And again, this is based on Hund's rule. We're deciding to pair the 3D before we pair the 4s. So looking at this, if we were going to make a copper plus ion, we would lose the 4s electrons first. And that would leave us with a complete 3D subshell. Therefore, B is not correct. Then looking at C, iron 2 plus ions contain 3 unpaired electrons. So again, let's write ion without the ions, so just iron on its own. That's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So then if we made our ion 2 plus, so that would be losing these 4s electrons, both of them, so we get 3d6. And then drawing the d subshells, we can work out how many unpaired electrons we have. So we first singularly fill each d subshell, and then we've got 3d6, so we need to add 2 electrons to one of our subshells. So that's going to be, if we put it in this first one, and then we count how many unpaired electrons we have. So we have 4 unpaired electrons, so C is not correct because it should be 4. And finally, looking at D, so scandium doesn't have different ions of oxidation states because this is a trait of a transition metal and scandium doesn't count as a transition metal. This is because it doesn't lose electrons to form an ion with an incomplete d subshell. Instead, the most stable ion for scandium is scandium 3+, which doesn't have an incomplete d subshell. It just loses all of the 3d and 4s electrons to form this ion. So it doesn't have this classic trait of a transition metal, and therefore it doesn't count as one, so it won't form ions with different oxidation states because it can't. It only has one ion that's stable enough to be formed. So D is also incorrect, and therefore we write A in the answer box. So to get the mark for this question, you need to write A in the answer box provided. The equation for combustion of C7H8 is shown in the following equation. C7H8 liquid plus 9O2 gas goes to 7CO2 gas plus 4H2O liquid. Enthalpy changes of formation are shown in the table. Calculate the enthalpy of combustion in kilojoules per mole for the hydrocarbon C7H8. A. Minus 3,914. B. Minus 692. D. Positive 692. Or D. Positive 3,914. Firstly, with this question, we need to write out the equation again. So C7H8 plus 9O2 goes to 7CO2 plus 4H2O. Then, using the enthalpy changes of formation, we can begin to construct what's called a Hess cycle. So for our hydrocarbon, that's going to be plus 12. Oxygen won't have one because it's already being formed in its base elements. Carbon dioxide, we're going to do 7 times minus 394. And then for water, we've got 4 times minus 286. So with a Hess cycle, that's just an alternative way of getting to the same root. So rather than doing this arrow here, we're going to go down here, along, and then up. So that means when the arrow goes the opposite way, we change the sign. So that's going to be minus 12 plus 7 times minus 394 plus 4 times minus 286, which equals minus 3,914 kilojoules per mole, which is the answer for A. We also know our answer is going to be negative, because it's combustion, which is an exothermic reaction, which means our enthalpy change for reaction will be negative if it's exothermic. To get the mark for this question, you must write A in the answer box provided. The diagram represents a Boltzmann distribution curve of molecules at a given temperature. Which statement for this Boltzmann distribution curve is correct at a higher temperature? A. The peak increases in height and moves to the left. B. The peak increases in height and moves to the right. C. The peak decreases in height and moves to the left. Or D. The peak decreases in height and moves to the right. On a Boltzmann distribution curve, the thing that's missing in this diagram is activation energy, which would be a line roughly here. And if we increase the temperature, which is what the question is asking us about, at a higher temperature, then more molecules are going to have an energy that's greater than the activation energy. So this is going to result in more successful collisions or more fruitful collisions. So if we want more molecules to have an energy greater than the activation energy, that's going to mean it's higher on this end. But the actual number of molecules hasn't changed, so the area under the curve needs to remain the same. So that means we're going to have a lower peak, which is shown here in this green line. So if we look at our different options, we need to match which one's showing the diagram that we've just drawn. So the peak is increasing in height and moving to the left. So our peak is moving to the right and it's decreased in height. So this is not correct. So we can cut out both that say increase in height because our peak is decreasing in height. And then we've got moves to the left and moves to the right. And as I've said before, we're moving to the right. So our answer is D. So to get the mark for this question, you need to write D in the answer box provided. A graph is plotted of ln k against 1 over T. K is equal to the rate constant and T is equal to temperature in Kelvin. The gradient has the numerical value of minus 55,000. What is the activation energy in kilojoules per mole? A. Positive 1.5 times 10 to the minus 7. B. Positive 2.22 times 10 to the negative 6. C. Positive 6.62. Or D. Positive 457. The key pieces of information in this question are the axes that we're plotting the graph on, the gradient, the numerical value of the gradient, and that we want activation energy in kilojoules per mole. So this question is looking at the Arrhenius equation. The Arrhenius equation is K equals A e to the minus EA over RT. We're going to be using it in a different form. We're going to be using it as ln K equals minus EA over R multiplied by 1 over T plus ln A. So this is in the form of Y equals mx plus C. So from this comparison, we can identify that m, or the gradient, is going to be minus EA over R, and that equals minus 55,000. So we can work out what EA is. EA is going to be equal to 55,000 multiplied by the gas constant, which is 8.314. And that equals 457,270 joules per mole. And we want our answer in kilojoules per mole, so we need to divide by 1,000. So we get EA is equal to 457.270 kilojoules per mole. So looking at the answers we're given, we want to match this, and that's going to be D. So to get the answer and the mark for this question, you need to write D in the answer box provided. The reversible reaction of nitrogen and hydrogen to form ammonia is shown below. In the equilibrium mixture, the partial pressure of N2 is 18.75 megapascals, and the partial pressure of H2 is 2.50 megapascals. The total pressure is 25 megapascals. What is the value of Kp in megapascals to the minus 2? A. 1.2 times 10 to the minus 4. B. 0.048. C. 0.075. Or D. 21. So first, let's highlight the key pieces of information in this question. So that's going to be the equilibrium equation, the partial pressure of N2 and the partial pressure of H2, the total pressure, and that we want the value of Kp. So if we write an expression for Kp, that's going to be Kp is equal to the partial pressure of ammonia, or NH3, squared, because it's got 2 in the stoichiometry of this reaction, then divided by the partial pressure of N2 times by the partial pressure of H2, which is going to be cubed because of the 3 molar ratio. So we already know the partial pressure of N2 and H2 at equilibrium, so we can work out the partial pressure of ammonia by using total pressure. So what we need to do is 18.75 plus 2.5, which equals 21.25, and then we do 25, which is the total pressure, minus 21.25, which gives us 3.75 megapascals, which is the partial pressure of ammonia. So then plugging in all these numbers, we can do 3.75 squared divided by 18.75 times by 2.5 to the power of 3, and that equals 0.048 megapascals to the minus 2, which is our value for Kp. So looking at the options we're given in this question, our answer matches answer B. So to get the mark for this question, you need to write B in the answer box provided. The equation for the reaction of ICl and H2 is shown below. The rate constant K for this reaction is 1.63 times 10 to the negative 6 decimeters cubed per mole per second. What is the overall order of the reaction? A, 0, B, 1, C, 2, or D, 3. If we start by writing a general rate equation, that's going to be rate is equal to K, which is the rate constant, multiplied by the concentration of one of our reactants and the concentration of another reactant. And then depending on the rate, so let's say we had a first order and a 0th order, that's going to mean the overall order of reaction is first order, because 1 plus 0 is 1. And so then we can kind of work out the units. So the way we do this is we do rate divided by A and then the concentration of B. But we wouldn't include the concentration of B if it was 0th order. And that's going to equal K. And we can work out the units of K to work out what our overall order of reaction is. So rate is measured in moles per decimeter cubed per second, and then concentration is moles per decimeter cubed. So if this overall reaction was first order, we could cancel out the moles per decimeter cubed and we would get a rate constant with the units of seconds to the minus 1. In the question, we have decimeters cubed moles to the minus 1, seconds to the minus 1, so it's not first order. So we can cross out B. It's not going to be 0th order, because 0th order would be having nothing on the bottom, and then we would get the same units as rate. So it's not 0th order. If we move on to second order, that's going to be divided by moles per decimeter cubed, moles per decimeter cubed, because both of our reactants would be to the power of 1, or one of them would be second order and one of them would be 0, but we're going to multiply concentration units twice for the sake of this example, let's say that both are first order, and so our overall reaction is going to be 0th order. And then we cancel out one of our concentration units, but the other one we don't because we can't cancel it out. And that's going to result in decimeters cubed moles to the -1 and seconds to the -1. That's because our decimeters cubed and moles are on the bottom, so we invert the indices. So the decimeters to the -3 becomes decimeters cubed, moles becomes moles to the -1, and then seconds will remain the same because it's on the top. It's not being divided by anything. And we can see that these units match our rate constant in this question. So our overall rate constant, or our overall order of reaction, is going to be second order, which is C. So to get the mark for this question, you need to write C in the answer box provided. 20 centimeters cubed of 0.1 moles per decimeter cubed hydrochloric acid is added to 10 centimeters cubed of 0.1 moles per decimeter cubed sodium hydroxide. What is the pH of the resulting mixture? A, 1.00, B, 1.18, C, 1.30, or D, 1.48? Firstly, in this question, let's highlight the key pieces of information. So that's going to be the volume and concentration of hydrochloric acid, the volume and concentration of sodium hydroxide, and the pH of the resulting mixture. So in this question, we're going to be using the equation triangle of number of moles is equal to volume times concentration. So working out number of moles of hydrochloric acid first, that's going to be 20 times 10 to the -3, because we're converting centimeters cubed into decimeters cubed, multiplied by 0.1, and that equals 2 times 10 to the -3 moles. Then if we do sodium hydroxide, that's going to be 10 times 10 to the -3 multiplied by 0.1, which equals 1 times 10 to the -3 moles. So we can already tell from just working out the moles that hydrochloric acid is in excess. So if we work out the excess moles of hydrochloric acid, that's going to be minusing these two. So that equals 1 times 10 to the -3 moles of excess H+, and that just means acid. So the equation we're going to use now is that pH is equal to minus log 10, the concentration of H+. So we work out the concentration of H+ by doing the number of moles divided by the total volume. So that's 20 plus 10 centimeters cubed, and then we convert it to decimeters cubed by timesing by 10 to the -3. And that equals 1/30 moles per decimeter cubed. So plugging this into the equation, we get pH is equal to minus log 10 of 1/30, which equals 1.48. So then if we try and match this to the options we're given for this question, this matches D, which is the answer for this question. And to get the mark for this question, you need to write D in the answer box provided. Iodide ions I- aqueous react with MnO4- aqueous. The unbalanced equation is shown below. What is the ratio of MnO2 solid to OH- aqueous in the balanced equation? A, 1:3, B, 1:2, C, 1:1, or D, 3:2? The common mistake that was made in this question is balancing the elements, putting a 2 here and circling B. But we also need to think about the charges in this question. So doing this method is incorrect for this question, and our answer is not going to be B. So in this question, we need to think about balancing the charges as well as the elements, and we can do this using oxidation and reduction and making half equations. So if we start with our reduction half equation, we're going to have MnO4-, and then we're going to add water and produce MnO2 plus OH minus. So the MnO4 is changing from an oxidation state of +7 to being +4. So it's being reduced. And now we can balance. So balancing this equation, we put a 2 in front of our H2O and we put a 4 in front of our OH minus. And then because we're reducing, we need to add 3 electrons in order to balance the charges, and also reduction is the gain of electrons. Next, we can look at our oxidation half equation, and that's going to be I minus plus OH minus, and that's going to produce IO minus plus H2O. So the reason we're using OH minus is because iodide is forming iodate in basic conditions. And this is an oxidation because we're going from a -1 oxidation state to a +1 oxidation state. So we're oxidizing, we are losing electrons. So balancing this equation, we put a 2 in front of our OH minus, and we need to add 2 electrons to balance the charge overall in this equation, or this half equation. So now we've written our half equations, we can begin to form our overall balanced equation. So the first thing we need to do is scale the electrons. So we need to have 6 electrons in both because the common number between 3 and 2 is 6. So rewriting our reduction half equation, that's going to be 6 electrons plus MnO4 minus, and we need 2 of these, plus 4 H2O, and that's going to produce 2 MnO2 plus 8 OH minus. So we've multiplied everything by 2. Now rewriting our oxidation half equation, we need to multiply everything by 3. So we have 3I minus plus 6 OH minus, and that's going to produce 3 OIO minus and 3 H2Os with 6 electrons. Then we cancel out. So we're going to cancel out the electrons from each side of the equation. We can also cancel out some of the OH minuses. So we can cancel out all of these 6 and then 2 from the reduction half equation. And then cancelling out some of the waters. So we can cancel out these 3 from the oxidation half equation and then 3 from the reduction half equation, leaving us with 1 water. So rewriting this overall balanced equation, we get 3I minus plus 2 MnO4 minus plus H2O, and then this goes to 3IO minus plus 2 MnO2 plus 2OH minus. So the question is asking us about the ratio of MnO2 to OH minus. So looking at the overall balanced equation that we've now produced, we can look at the ratios. We've got a 2 and a 2. So a 2 to 2 ratio is also a 1 to 1 ratio, and that's C. So to get the mark for this question, you need to write C in the answer box provided. Which statement or statements is or are correct when a catalyst is added to a system in dynamic equilibrium? 1. The rates of the forward and reverse reactions increase by the same amount. 2. The concentrations of the reactants and products do not change. 3. The value of Kc increases. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So firstly with this question, let's look at each statement individually and determine if it's correct or not. So when you add a catalyst to a dynamic equilibrium, the rates of the forward and reverse reactions increase by the same amount. This is true. The forwards and reverse reactions might be favoured if you change temperature, pressure, or the amount of your reactant or product. So that one is correct because they don't change when you have a catalyst. The concentrations of the reactants and products don't change. This is also true because you're not adding any more reactant or product, you're not changing the volume or anything like that. So they do stay the same, so they don't change. Then the value of Kc increases. So Kc is based on concentration. So if we had a basic equilibrium where we've got A plus B, a dynamic equilibrium C plus D. So Kc is equal to the concentration of C multiplied by the concentration of D divided by the concentration of A multiplied by the concentration of B. And then if you had, let's say, 2 of A and 3 of C, you would have a squared and a cubed here. But this is based on concentration, and we've already established that the concentrations don't change. So Kc won't increase, because for it to increase, you would need more of C and D. So you need a higher concentration of your products. But because they don't change, it's not going to increase. And therefore, this is incorrect. So we're looking for an answer that says 1 and 2, and that is B. So we write B. And to get the mark for the question, you need to write B in the answer box provided. Which statement or statements for group 2 elements is or are correct? 1. The second ionization energy of magnesium is greater than the second ionization energy of calcium. 2. A strontium ion, Sr2+, contains a total of 6 electrons in s orbitals. 3. The equation for the reaction of barium with water is 2Ba plus 2H2O goes to 2BaOH plus hydrogen. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So we're going to look at each of these questions individually. So looking at the first statement, the second ionization energy of magnesium is greater than the second ionization energy of calcium. So this statement is correct, and that's because calcium is larger than magnesium, or magnesium is smaller. And because magnesium is smaller, it's got a greater nuclear attraction, and that's because it's closer to the nucleus, so it's going to require more energy to remove another electron and create this Mg2+ ion. So this first statement is correct, and so we can eliminate C as a possible answer. Then looking at number 2, strontium ion Sr2+ contains a total of 6 electrons in s orbitals. So if we write out the electron configuration for strontium first, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, 4s2, 3d10, 4p6, 5s2. And because we're making a 2+ ion, we need to remove 2 of these electrons, and that's going to be our 5s2 electrons we remove. So if we then count how many electrons are in s orbitals, we have 2, 4, 6, 8. 8 electrons in s orbitals. So it's not 6, it's 8. So this statement is not correct. So we can eliminate A and B. So now finally looking at 3, we know it's going to be wrong because we can't have it being right, but we do need to double check. So barium is in group 2, so its hydroxide is going to be BaOH2 in order to balance it, because OH has a 1- charge and Ba has a 2+. And then we're going to add hydrogens, these are our products, and we're reacting with barium and water. So balancing this equation, we need 2 waters. So this is the correct reaction of barium with water and not the one we've been given in number 3. So this is also not correct. So that means our answer is D, and to get the mark for this question, you need to write D in the answer box provided. Which statement or statements for the complex ion CO, NH2, CH2, CH2, NH2 brackets 3, 2 plus, is or are correct? 1. It has cis and trans isomers. 2. It has optical isomers. 3. It is 6-fold coordination. A, 1, 2 and 3, B, only 1 and 2, C, only 2 and 3, or D, only 1. So for this question, let's start by drawing the complex. So we have cobalt in the middle, and then we've got this 6-fold octahedral shape, which we can show with different wedges, and we have NH2 joined to each wedge. So then we need to put the rest of the ligand on. So we have this ethyl chain, which we can draw on. So we could have it looking like this, where the nitrogens are connected by this skeletal ethyl chain of CH2, CH2. And then we need to put the charge on. So looking at the different options we're given, it has cis-trans isomers. Well, this statement is incorrect because in order to have cis-trans isomers, you need to have different priority groups. And because we've got the same bidentate ligand attached, we don't have different groups, so it can't have cis-trans isomers. We do have 6-fold coordination, which is shown with the wedges in this question. And now we need to see if it has optical isomers. So it will, if we did a mirror image, we would have the ethyl groups going like this in the gaps of our structure. And that is just the mirror image, which will be our optical isomer. So looking at the options we're given, well, it's not 1, so we can cross out A, B, and D. So it must be C, and this does track with us saying it has optical isomers and 6-fold coordination. So what we are thinking does match the options. So we can put C. And to get the mark for this question, you need to write C in the answer box provided. This question is about magnesium bromine and magnesium bromide. Part A. Relative atomic mass is defined by the weighted mean mass compared with 1/12 mass of carbon-12. Explain what is meant by the term weighted mean mass. So this question is about recall, and you've got to recall the definition for the weighted mean mass. So that is the mean taking into account the relative abundances of the isotopes. So in order to get the mark for this question, you need to write this sentence: the mean taking into account relative abundances of the isotopes. If you got this question wrong, I'd recommend making a revision resource with this statement on it so that you can remember it for the future. Part B, Part 1. Draw a dot and cross diagram for MgBr2. Show outer electrons only. So magnesium bromide is ionically bonded. So we need to draw an ionic bonding diagram that's dot and cross. So if we start by drawing magnesium, magnesium will have an empty outer shell and a 2+ charge because it's going to be lending 2 electrons to bromine. But we have 2 bromines, so each one gets 1 electron from magnesium, and then we complete its outer shell with its existing 7 electrons. And bromine has a negative charge, so this is the completed ionic bonding diagram for magnesium bromide, and to get the 2 marks for this question, you must have drawn this diagram, where you get 1 mark for the charges and then 1 mark for the outer electrons in this question. Part 2. Calculate the total number of ions in 1.74 grams of magnesium bromide, MgBr2. Give your answer to 3 significant figures. Firstly, with this question, we need to highlight the key pieces of information. So firstly, that we want the total number of ions, the mass of magnesium bromide we have, and that we need to give our answer to 3 significant figures. So the first equation triangle, and the only equation triangle we're going to use in this question, is mass is equal to the number of moles times the relative formula mass. So this is what we're going to do first. We're going to work out the number of moles. And we can do this using the mass of magnesium bromide, and we can calculate its relative formula mass. So that's going to be 1.74 grams divided by 24.3 plus 2 times 79.9. So that's the relative atomic mass of magnesium plus 2 of the relative atomic masses of bromine. And that equals 9.45 times 10 to the negative 3 moles of MgBr2. But we want the number of ions, and in magnesium bromide there are 3 different ions. There's magnesium and then there's 2 bromine ions. So we need to multiply this number by 3. So we do 9.45 times 10 to the negative 3 multiplied by 3, and that gives us 0.0283 moles. Then finally, because we want the total number of ions and not moles, we need to multiply by Avogadro's constant. So that's 0.0283 multiplied by 6.023 times 10 to the 23. And that equals 1.71 times 10 to the 22 ions. So that's our answer to 3 significant figures, which we can then put on the answer line for this question. So 1.71 times 10 to the 22. So to get the 3 marks for this question, you get a mark for working out the number of moles of magnesium bromide, a mark for multiplying this by 3, and then a mark for working out the number of ions to 3 significant figures. Part C. Table 16.1 shows some physical properties of magnesium, bromine, and magnesium bromide. Explain the physical properties shown in Table 16.1 using your knowledge of structure and bonding. So firstly, let's look at magnesium. So the structure of magnesium is it's a giant lattice and it's metallically bonded. In metallic bonding, you have delocalized electrons which can carry a charge. And that's why if we look at table 16.1, we're told that magnesium is a good electrical conductor as a solid and a liquid. Then if we start to look at bromine, so bromine, its structure is simple molecular. So this means it's held together with London forces between the molecules, and it can't conduct, which we're told in table 16.1 because it's a poor electrical conductor as a liquid and a solid. Finally, if we move on to look at magnesium bromide, so starting again with its structure, magnesium bromide has a giant lattice structure and it's ionically bonded, which we covered in a previous question. So this is between oppositely charged ions. In a solid, the ions can't move, but in the solution, the ions can move. And in solution or as a liquid, when they're moving, they can conduct a charge. So that's why in the table we've got it's a poor electrical conductor as a solid, but a good electrical conductor as a liquid. Then we need to look at why the melting points are different, because we've covered electrical conductivity, but we haven't done anything about melting points yet. On table 16.1, we can see that magnesium and magnesium bromide have the higher melting points, and then bromine has this very low melting point in comparison. So looking at the different bonds, that's going to be why the melting points are different, because you need different amounts of energy to break these different bonds. So metallic and ionic bonds are a lot stronger than London forces, which is in bromine. So the metallic and ionic bonds in magnesium and magnesium bromide take a lot more energy to break. This is a level response question shown by the asterisk. So in order to get the 6 marks for this question, you need to explain all 3 melting point values and conductivities in terms of structure, bonding, particles, and the relative strengths of the forces, which we have done in this question. But you also need to have a well-developed line of reasoning, which is clear and logically structured, which we also have in this question. But because it's a level response question, there aren't specific marking points. It's the way you lay out your question and how accurate it is. Part D. The enthalpy change of hydration of bromide ions can be determined using the enthalpy changes in table 16.2. Part 1. An incomplete energy cycle based on table 16.2 is shown below. On the dotted lines, add the species present, including state symbols. So if we start with the formation of magnesium bromide, which is going to be in this part here. So that's magnesium as a solid and bromine as a liquid. It's very important that you write a liquid state symbol here. And then we're going to look at the second ionization of magnesium, which is in this part here. So that's going to be Mg2+ as a gas, and then 2Br as a gas also, with 2 electrons. So to get the 2 marks for this question, you get a mark for each correct equation that you've written for this question. Part 2. Using your completed energy cycle in 16D1, calculate the enthalpy change of hydration of bromide ions. So for this question, I think it's better if we return to the previous part of the question, where we've got our energy cycle that's now completed. So the first thing we should do with this question is fill out the numbers that we already know, which are here, and assign them to an arrow. So if we start at the bottom left, that's going to be minus 186, which is the solution of magnesium bromide, because you're going from this magnesium bromide solid to being 2 different ions in solution. Then if we move on to the arrow above, that's going to be minus 525, which is the formation of magnesium bromide, because you're going from its base states in order to form this magnesium bromide solid. Moving up, you get 2 times 112, and that is the atomization of bromine, but we've multiplied it by 2 because we've got 2 bromines that we're atomizing. Moving up again, we have 148. So this is the atomization of magnesium, because you're going from magnesium solid to magnesium gas. Then moving up again, you get 736, which is the first ionization energy of magnesium, because you're forming this Mg+. And then the top left is going to be 1450, which is the second ionization energy of magnesium, because you're forming this 2+ ion. Then if we look at the other side, if we look at the right and we work our way down, we've got 2 times minus 325, which is the electron affinity of bromine, because we're forming these Br- ions and we're forming 2 of them, so we multiply by 2. And finally, this other arrow, we've got minus 1926, which is the hydration of magnesium ion, because we're going from this Mg2+ gas to Mg2+ aqueous, so we're hydrating it. And then this final arrow is the one we want to work out, which is the hydration of the bromide ion, but we're actually going to have to divide by 2 because we've got 2 bromide ions that we are hydrating. So we just need to remember to divide our final answer by 2. So the next step we need to do is we need to work our way around this energy cycle to get our number. So rather than doing this arrow, we're going to go a slightly longer way around the energy cycle. and wherever the arrow is going in the opposite direction, we flip the sign. So that's going to be positive 1926 plus 2 times 325 minus 1450 minus 736 minus 148 minus 2 times 112, and then we're going to minus 525, the sign is staying the same now, and minusing 186. So this equals minus 693 kilojoules per mole. Then dividing by 2, we get minus 346.5 kilojoules per mole. So this is the answer for this question once we've divided by 2, which we can write on the answer line provided, so minus 346.5. To get the 2 marks for this question, you get a mark for calculating minus 693, and then you get a mark for dividing by 2 and getting your final answer of minus 346.5. Part 3. Write the equation for the lattice enthalpy of magnesium bromide and calculate the lattice enthalpy of magnesium bromide. So let's start with the equation for the lattice enthalpy of magnesium bromide. So this is a little bit of recall in terms of what a lattice enthalpy equation is. So it's where you get your ions, so Mg2 plus as a gas, to Br minus as a gas, and you form your solid. So that's going to be MgBr2 solid. So similar to the last question, we need to go back to our energy cycle. So if we look here, we're going from this point to this point. So we're going to do a little arrow around like this. So doing the calculation, that's going to be minus 1926 plus 2 times minus 346.5, because that's what we calculated in the previous question, and we're multiplying by 2 because 2 bromines. And then we're going to add 186 because the arrow is going in the opposite direction. So that's going to equal our lattice enthalpy, which we can then transfer the calculation onto here. So if we rewrite that, it's going to be minus 1926 plus 2 times minus 346.5 and then plus 186. So that equals minus 2,433 kilojoules per mole, which we can then write on the answer line, minus 2,433. So to get the 3 marks for this question, you get a mark for your equation being correct, and you get a mark for the lattice enthalpy calculations being correct, and a mark for your answer. Methanol, CH3OH, can be made industrially by the reaction of carbon monoxide with hydrogen as shown in equilibrium 1. Part A. Predict the conditions of pressure and temperature that would give the maximum equilibrium yield of methanol in equilibrium 1. Explain your answer. So firstly, we want to be producing more methanol to get a maximum equilibrium yield. So we want to favour the right-hand side of this reaction, or this equilibrium. The right-hand side has fewer gaseous moles. So in order to push it and favour the right-hand side, we need to have a high pressure. The forwards reaction is exothermic, and to favour the forwards reaction, we need a low temperature. So to get the 3 marks for this question, you get a mark in this question for saying that the right-hand side has fewer gaseous moles. You get a mark for saying that the forwards reaction is exothermic, and then you get a mark for saying high pressure, low temperature. Part B. A catalyst is used in the production of methanol in equilibrium 1. State 2 ways that the use of catalysts helps chemical companies to make their processes more sustainable and less harmful to the environment. So the first way that catalysts mean that the process is more sustainable and less harmful to the environment is that they result in a lower energy demand. And the second way is that you've got less carbon dioxide emissions or less fossil fuel emissions. So these are the 2 points to get the 2 marks in this question. Part C. Standard entropy values are given below. A chemist proposed producing methanol at 525 Kelvin using equilibrium 1. Explain with a calculation whether the production of methanol is feasible at 525 Kelvin. So the first thing we need to do is work out delta S. So that's going to be the products of the equilibrium minus the reactants. So that's 238 minus 198 plus 2 times 131. Because if we look at equilibrium 1, that would be CO plus 2H2 equilibrium CH3OH. So we can see how we've multiplied by 2 because we've got these 2 hydrogens. So delta S is going to be equal to minus 222 joules per Kelvin per mole. But as standard, we usually go with kilojoules. So that's going to be minus 0.222 kilojoules per mole per Kelvin. So now we're going to use an equation, and that equation is delta G equals delta H minus T delta S. So plugging in the numbers to work out delta G, that's going to be minus 91, because that's what we're told in the question, minus 525 multiplied by minus 0.222, which equals 25.55 kilojoules per mole. So looking at where these numbers come from, this minus 91 is the delta H value for equilibrium 1, and it equals minus 91 kilojoules per mole. So that's why it's better to convert joules into kilojoules, because then you are changing less things that you're given in the question. And then you're minusing your temperature, which is told in the question is 525 Kelvin, and then you're multiplying by your delta S that you've just calculated in order to get this final answer of 25.55 kilojoules per mole. Now we need to talk about whether the reaction is feasible or not, and this reaction is not feasible. So the reason for this is because the Gibbs free energy, or delta G, is bigger than 0, so it's a very positive number, which means it's not feasible. To get the 5 marks for this question, you get a mark for using the delta S equation, you get a mark for calculating minus 222 or minus 0.222. You get a mark for using the delta G equation. You get a mark for calculating 25.55, and then you get a mark for saying not feasible because delta G is bigger than 0. Part D. At 298 Kelvin, the free energy change delta G for the production of methanol in equilibrium 1 is minus 2.48 times 10 to the 4 joules per mole. Delta G is linked to Kp by the relationship delta G equals minus RT ln Kp, where R is the gas constant and T is temperature in Kelvin. Calculate Kp for equilibrium 1 at 298 Kelvin and give your answer to 3 significant figures. The first thing we're going to do in this question is highlight the important bits of information. So firstly, the temperature we're given, the joules per mole or the delta G value, then that we have this equation, what each one stands for in the equation, so R is gas constant and T is temperature, and we need to calculate Kp for equilibrium 1 to 3 significant figures. So the first thing we're going to do in this question is rearrange the equation that we're given for ln Kp. So that's going to be ln Kp is equal to delta G divided by minus RT. So then we can plug in the numbers. So we can do 2.48 times 10 to the 4, and that's from this delta G value we're given in the question. Then divided by negative 8.314 multiplied by 298, which equals 10.01. And that's ln Kp. But we don't want ln Kp, we want Kp on its own. So to work out Kp, we need to do e to the 10.01, which equals 2.22 times 10 to the 4. Now we need to work out units, because there's a space in the question for units. And this is our answer to 3 significant figures. So that's good, we've answered that bit. But in terms of units, if we were to write an expression for Kp, that's going to be Kp is equal to the partial pressure of methanol, so CH3OH, divided by the partial pressure of carbon monoxide times the partial pressure of hydrogen squared. And that's taken from equilibrium 1. So if we write that out again, that's going to be carbon monoxide plus 2 hydrogens equilibrium to methanol. So we can see where the 2 is coming from, that's being the squared in this Kp. Then if we say that each one is measured in atmospheres, so that's going to be an atmosphere on the top, atmosphere on the bottom times atmosphere squared. We can cancel out these 2, so we're left with atmospheres to the minus 2 as our units, which we then write on the line, so ATM to the minus 2, and then 2.22 times 10 to the 4. To get the 3 marks for this question, you get a mark for using the rearranged equation and getting 10.01 and working out ln Kp. You get a mark for working out Kp, and then you get a mark for your units. This question is about reactions and uses of the weak acids methanoic acid, HCOOH, and ethanoic acid, CH3COOH. Part A. A student adds magnesium metal to an aqueous solution of ethanoic acid, CH3COOH. A redox reaction takes place. Write the overall equation for this reaction and explain in terms of oxidation numbers which element has been oxidized and which element has been reduced. So firstly, let's write the equation. So we're told we're adding magnesium metal to ethanoic acid and a redox reaction is taking place. So let's start with our reactants. We've got magnesium and ethanoic acid, CH3COOH. Then we're going to produce magnesium ethanoate. So that's CH3COO. This has a -1 charge, so we need 2 of these because magnesium has a 2+ charge. And then we're going to add hydrogen. So then we need to balance the equation. To balance the equation, we need to add a 2 in front of the ethanoic acid. Next, we need to look at oxidation numbers and work out the element being oxidized and the element being reduced. So looking at magnesium first, any element in its base form will have an oxidation number of 0. Then CH3COO has a -1 oxidation number as this ion, this ethanoate ion. So that means for it to have an overall charge of 0, hydrogen will have a +1 oxidation number. So again, this ion has a -1 oxidation number, and there are 2 of them, so that's effectively -2. So magnesium must have a 2+ oxidation number. in order for this to be 0. And then hydrogen, it's another element on its own, so it's going to have an oxidation number of 0. Now we need to look at which elements being oxidized. So oxidation is the loss of electrons, so that's going to be an oxidation number increase, so it's going to get bigger. And that's going to be magnesium. So magnesium is being oxidized because its oxidation state is going from 0 to +2, as we can see in the equation in purple. Then we need to look at reduction. So this is where you gain electrons and your oxidation number decreases. So that's going to be hydrogen. And that's because hydrogen's oxidation numbers are going from +1 to 0. So to get the 3 marks for this question, you get a mark for your equation, you get a mark for the correct element being oxidized and the correct element being reduced. Part B. The Ka values of methanoic and ethanoic acid are shown in table 18.1. A student adds methanoic acid to ethanoic acid. An equilibrium is set up containing 2 acid-base pairs. Complete the equilibrium and label the conjugate acid-base pairs as A1, B1 and A2, B2. So the first thing we need to do with this question is work out which is the stronger acid. So pH is calculated with -log 10, the concentration of H+, and pKa is equal to -log 10 of Ka. And pH and pKa are equal to each other. So we can work out pKa. So working out pKa, you get 3.74 and 4.75. So we can tell that methanoic acid is the stronger acid because it's got a lower pH. So then if we're going to label the acid and the base, we can label A1 and B2. So then finishing the equilibrium, we know that methanoic acid is the stronger acid, so it's going to produce the negative ion of HCOO-. And then ethanoic acid is going to gain this hydrogen because bases are proton acceptors and acids are proton donators. So then this is going to be CH3COOH2+. Now we need to label the acid and base conjugate pair. So we have B1 and A2. To get the 2 marks for this question, you get a mark for the equilibrium and then you get a mark for your conjugate acid-base pairs. Part C. Use table 18.1 to answer the following questions. Part 1. The student measures the pH of ethanoic acid as 2.72. Show that the concentration of ethanoic acid is 0.204 moles per decimeter cubed. So the first thing to do with this question is highlight the important pieces of information. So first key piece of information is that we've got a pH of 2.72 and we have a concentration of 0.204 moles per decimeter cubed that we're trying to show. So the first equation we're going to use is the equation for working out the concentration of H+. So that's 10 to the negative pH. So that equals the concentration of H+. Then the second equation we're going to use is that the concentration of H+ multiplied by the concentration of A- divided by the concentration of HA is equal to Ka. So when HA, this is a weak acid, when it dissociates, it forms an equilibrium of H+ and A-, which we saw in the previous question with these conjugate acid-base pairs. And the concentrations of H+ and A- are going to be equal in this equilibrium. So to make our lives easier, we can rewrite this numerator as the concentration of H+ squared. Now we can use these 2 equations to start working out the concentration of ethanoic acid, which is going to be this HA. This is going to be CH3COOH as its concentration, which hopefully should be 0.204 moles per decimeter cubed. So starting off with this first equation, 10 to the negative pH. So that's going to be 10 to the minus 2.72. And that equals 1.905 times 10 to the negative 3 moles per decimeter cubed. So that's the concentration of H+. Then we want to rearrange for HA, or the concentration of ethanoic acid, so CH3COOH, is going to be equal to the concentration of H+, which we've just worked out, is 1.905 times 10 to the negative 3, and this is going to be squared. Then we're going to divide by Ka. So we've flipped these two around in our equation, and Ka we're given in table 18.1, so that's going to be 1.78 times 10 to the negative 5. So this equals 0.204 moles per decimeter cubed, which is what we should have gotten because we're told this is the concentration in the question, and we've effectively shown this in our working out. To get the 2 marks for this question, you get a mark for working out the concentration of H+, and a mark for working out the concentration of ethanoic acid correctly as 0.204 moles per decimeter cubed. Part 2. The student plans to make a buffer solution of pH 4.00 from a mixture of ethanoic acid and sodium ethanoate. The student mixes 400 centimeters cubed of 0.204 moles per decimeter cubed ethanoic acid with 600 centimeters cubed of sodium ethanoate. Calculate the concentration of sodium ethanoate needed to prepare this buffer solution of pH 4.00. So I've just copied across table 18.1 to help us in this question. But the first thing we need to do with this question is highlight the key pieces of information. So we've got 400 centimeters cubed of 0.04 moles per decimeter cubed ethanoic acid, 600 centimeters cubed of sodium ethanoate, a pH of 4, and we want the concentration of sodium ethanoate needed to prepare this buffer solution. So like the previous question, we're going to use the equation of 10 to the minus pH is equal to the concentration of H+, but this is going to be the concentration of H+ in the buffer. So calculating this, we get 10 to the minus 4, which equals 1 times 10 to the negative 4 moles per decimeter cubed. Then we're going to work out the concentration of ethanoic acid in the buffer. So the way we're going to do this is we're going to do 0.204 divided by 1. So what we've done is we've got the total volume, which is 1,000, because 400 plus 600 equals 1,000, and this is centimeters cubed, which equals 1 decimeter cubed. So we've divided the concentration by the total volume, and then next we're going to scale it. So we've got 400 centimeters cubed, which is 0.4 decimeters cubed, and that equals 8.16 times 10 to the negative 2, and that is the concentration of ethanoic acid in the buffer. So now, like the last question, we're going to use the equation of H plus multiplied by A minus divided by HA is equal to Ka. So before we get on to this, let's work out what we actually have already in this question. So if we plug in the numbers, we have our concentration of H+, we have 1 times 10 to the negative 4. We don't have our A minus, but our A minus can be rewritten as CH3COO minus. Then we can divide by the concentration of HA, which is going to be 8.16 times 10 to the minus 2. And we can make this equal to 1.78 times 10 to the minus 5, which is our Ka for ethanoic acid. Rearranging this for the concentration of this A minus or this ethanoate ion, we're going to get that CH3COO minus is equal to 1.78 times 10 to the minus 5 multiplied by 8.16 times 10 to the minus 2 divided by 1 times 10 to the minus 4. So this equals 1.5 times 10 to the minus 2, and this is moles per decimeter cubed of CH3COO minus in our buffer. Now, like what we did for ethanoic acid, but instead we worked out the concentration in the buffer by scaling based on its volume, here we're trying to go from the buffer to the original. So we're going to do the opposite to what we did at the beginning. So taking the calculator value, which is 1.452, etc., times 10 to the minus 2. So we've written 1.5 here for convenience, but this is the calculator value and you should have saved this on your calculator. Then we're going to divide by 0.6, which is 600 centimeters cubed in decimeters cubed. So where we've multiplied in this first step, we're doing the opposite. In terms of the 1, we can multiply by 1 at the top or the numerator. It doesn't make much difference, the same way dividing by 1 doesn't make much difference, but for understanding, we are going to multiply by 1 at the top. And then this equals 2.4 times 10 to the minus 2, which is the concentration of sodium ethanoate initially. So that's what we can write on the answer line, 2.4 times 10 to the minus 2. To get the 4 marks for this question, you get a mark for calculating the concentration of ethanoic acid in the buffer, so 8.16 times 10 to the negative 2. You get a mark for working out the concentration of H plus in the buffer, so 1 times 10 to the negative 4 moles per decimeter cubed. You get a mark for working out the concentration of sodium ethanoate in the buffer, so 1.5 times 10 to the negative 2 moles per decimeter cubed. And then you get your 4th and final mark for working out the concentration of sodium ethanoate in the initial solution, which is 2.4 times 10 to the negative 2. Standard electrode potentials for 4 redox systems are shown in Table 19.1. Part A. A student sets up a standard cell in the laboratory based on redox systems 3 and 4. Draw a labelled diagram to show how this cell could be set up to measure its standard cell potential at 298 Kelvin. The first thing to do with this question is to draw a basic setup for these redox systems and to show this cell. So what we're going to have is firstly 2 beakers of roughly similar size. You're going to have your 2 electrodes in each, one in each beaker, a voltmeter connecting them, and a salt bridge. So the salt bridge needs to be labelled as the salt bridge, and then we are going to look at the specifics of what makes up each half cell. So we're told in the question we're using redox systems 3 and 4. So if we look at 3 and 4, we can see that we've got silver and silver ions in redox system 3. So we're going to have a silver electrode and silver ions in the solution, and they're going to be 1 mole per decimeter cubed concentration. Then looking at redox system 4, we don't have any solid metals, so we're going to have a platinum electrode, and all of the ions are going to be in this solution. So we've got MnO4 minus, H plus, and Mn2 plus. And they also have a 1 mole per decimeter cubed solution concentration. To get the 3 marks for this question, you get a mark for your voltmeter and salt bridge. You get a mark for each half cell, so the silver half cell and then the one with platinum and all of your ions. Part B. A student warms a mixture of methanol, HCHO, and acidified potassium manganate 7. The student observes gas bubbles. Explain this observation in terms of electrode potentials and equilibria. Include overall equations in your answer. So, looking at the redox systems that involve methanol and potassium manganate 7, so the manganate 7 ion, that's 1, 2 and 4. So the electrode potential of redox system 4 is a lot more positive than redox systems 2 and 1 because they have negative values and redox system 4 has a very positive value. So the more negative systems, which are going to be number 2 and number 1, what's going to happen with their equilibrium is they're going to shift left because these are a lot more negative. It's minus 0.11 and minus 0.03 versus 1.51, which is a lot more positive, and it's going to shift right. Redox system 4 is going to shift right. Now we need to look at writing our overall equations. So if we start with looking at redox systems 2 and redox systems 4, so we know that redox system 2 is going to shift left, so we can rewrite this equilibrium. So we have HCHO, or methanol, plus H2O, and that's going to produce methanoic acid, or HCOOH, plus 2H plus, and then 2 electrons. Then rewriting redox system 4, we get MnO4 minus plus 8H plus 5 electrons, and that produces Mn2 plus 4H2O. So this one's shifted right. Now we need to scale the two equations so that the electrons have the same number. So the common number between 5 and 2 is 10. So if we change these to 10, that means we've got to multiply the top equation by 5. So we have 5, 5, 5, and then 2 times 5 is 10. And then on the bottom, we multiply everything by 2. So we've got 2, then 16, 2, and 8. Then we cancel some things. So the electrons can be cancelled because they're the same species and they're on opposite sides of the equation. Some of the waters can be cancelled, so these 5 and then 3 is left. Then we can cancel some of the H pluses, so this 10, and then we're left with 6. So if we write the overall equation for redox systems 2 and 4, we get 5HCHO plus 2MnO4 minus plus 6H plus, and that produces 2Mn2 plus 5HCOOH and 3 waters. Now we're going to do the same for 1 and 4. So rewriting redox system 1. So again, this one's shifting left. So we have HCOOH going to CO2 plus 2H plus 2 electrons. Then rewriting redox system 4. So we have MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. So like the last one, we need to scale the electrons. So we have 10 and 10. multiplying the top one by 5, so we got 5, 5, and then 10. The bottom one by 2, so we have 2, 16, 2, and 8. Then we can cancel out some things. So we can cancel out the electrons. Then we can cancel out some of the protons, so some of the H pluses. So this 10 can go, and then we're left with 6. Then we can cancel nothing else. So we can write our overall equation. So we have 5HCOOH plus 2MnO4 minus plus 6H plus, and then that's going to produce 2Mn2 plus 5CO2 or 5 carbon dioxides and 8 waters. So here we've written our two overall equations. So we can see in this second equation why we might expect to see gas bubbles, because we're going to produce carbon dioxide, which is a gas. To get the 4 marks for this question, you get a mark for comparing electrode potential values, a mark for talking about how the equilibrium is going to shift, and then you get a mark for each overall equation that you've written. Part C. Methanoic acid, HCOOH, can be used in a fuel cell. As with all fuel cells, the fuel methanoic acid is supplied at one electrode and the oxidant, oxygen, at the other electrode. The standard cell potential for this fuel cell is 1.34 volts. The overall reaction is shown below. Using the information in table 19.1, deduce the half equation for the reaction at the oxygen electrode and calculate the standard electrode potential for the oxygen half cell. So let's highlight the key piece of information. We have the standard cell potential for the fuel cell and the overall reaction. And we're told to use table 19.1. So we want to work out the half equation for the reaction at the oxygen electrode and calculate the standard electrode potential for the oxygen half cell. So firstly, we need to look at table 19.1 and look at which redox system has the most similar things to this overall reaction. So the most similar species is going to be redox system 1. So redox system 1 is very negative, and we can already tell that it's been shifted left because the methanoic acid is on the left of this overall reaction. So if we rewrite this, we have HCOOH going to CO2, 2H plus, and 2 electrons. So we know we've got to have 2 electrons here because they cancel out, and 2 H pluses because you can see that there aren't any electrons or H pluses in this overall reaction, so they cancel out exactly. So we need the same amount and on opposite sides of the equation. Then we need to write the species missing, so that will be half O2, and then it goes to H2O. So this is going to be our oxygen half cell equation. So we can write this half equation down. We can do 2E minus, or 2 electrons, plus 2H plus half O2 or oxygen goes to form H2O or water. Then we need to calculate the standard electrode potential. So that's going to be 1.34 plus minus 0.11. So that's the overall fuel cell standard electrode potential plus the redox system's electrode potential of minus 0.11, and that's going to equal plus 1.23 volts, which we can write on the answer line. So it's important to write this plus because they've done it in the table. You won't lose a mark if you don't write it, but in the future it's really important to add this positive charge. So to get the 2 marks for this question, you get a mark for your half equation and you get a mark for your standard electrode potential value. A student investigates the reaction between ethanoic acid and methanol in the presence of an acid catalyst. The equation is shown below. Part A. The student carries out an experiment to determine the order of reaction with respect to ethanoic acid. The student uses a large excess of methanol. The temperature is kept constant throughout the experiment. The student takes a sample from the mixture every 20 minutes and then determines the concentration of ethanoic acid in each sample. From the experimental results, the student plots the graph below. Part 1. Explain why the student uses a large excess of methanol in this experiment. So the reason that the student is using such a large excess of methanol is so that its concentration is constant. So to get the mark for this question, you can write this statement. They will also accept saying that zero order with respect to methanol, or to ensure equilibrium is far to the right. So one of these three statements will get the mark for this question. Part 2. Use the half-life of this reaction to show that the reaction is first order with respect to ethanoic acid. Show your working on the graph and below. For this question, we need to go back to looking at the graph, and we're going to work out half-lives. So the first thing to do when working out half-lives is to draw a line of best fit. So this line has to go through as many points as possible, and we're going to curve slightly towards the end of this line of best fit. So then we need to work out half-lives. So if we start with the concentration of 4, half of this is 2. So then we read off on the graph where it intersects with this line of best fit and read off the minutes. So for 4, that's going to be this point here. Reading this off, we get 36 minutes. Then looking at number 2, so that's going to intersect here at 140 minutes. So we do 140 minus 36, which equals 104 minutes as our first half-life. But we need to do more than one. So if we do 5 and then 2.5, which would be here, reading off from 5 we have 0, and then 2.5, reading that off here, this is going to be 104. So our second half-life is 104 minutes. So if we go back to part 2, so we have 2 half-lives, and they're going to equal 104 minutes. So the fact that they're constant, well, that's going to indicate that it's a first order reaction. So if constant half-lives, so it's first order. To get the marks for this question, you get a mark for working out the half-lives, so 104 minutes, but it can be in the range of 102 minutes to 110 minutes. And then you get your second mark for saying that constant half-lives mean that it's first order. Part 3. Determine the initial rate of reaction. There are 2 methods to working out initial rate of reaction. The first one involves using the graph. So if we go back and look at the graph, I've drawn a tangent at the time equals 0, and then we're going to work out the gradient of the tangent. So if we use 2 and 4 again as our y values, reading off from 4, that's this green line here, and that's going to be 30 minutes. And then looking at 2 and reading off from 2, that's here, and that's going to be 92 minutes. So if we work out our gradient, so the units on the y-axis are times 10 to the negative 3 moles per decimeter cubed. So our numerator is going to be 4 minus 2 times 10 to the negative 3, then divide by 92 minus 30, which equals 3.23 times 10 to the negative 5 moles per decimeter cubed per minute, which we can write on the answer line, 3.23 times 10 to the negative 5. Now looking at the second way we could have answered this question. So the second way to do this is using the equation of K equals ln2 divided by the half-life. So the half-life is 104 minutes, which we've worked out. So that's ln2 divided by 104, which equals 6.66 times 10 to the negative 3 minutes to the minus 1. Then we multiplied by the initial concentration. So looking at the graph, that's going to be 5 times 10 to the negative 3. So if we do 6.66 times 10 to the negative 3 multiplied by 5 times 10 to the negative 3, we get 3.33 times 10 to the negative 5 moles per decimeter cubed per minute. So we can see that both of these methods get a relatively similar answer, and the mark scheme will accept any value in the range of 2.9 times 10 to the negative 5 to 4 times 10 to the negative 5. So there's quite a big range, and both of these values are in that range, so it doesn't matter which method you use as long as you do it correctly. So in method 1 you get your 2 marks from 1 drawing the tangent and 2 working out the gradient of the tangent. In method 2 you get your marks for working out k and then multiplying by 5 times 10 to the negative 3. Part B. The student carries out a second experiment to determine the value of Kc for this reaction. The student mixes 9.6 grams of methanol with 12.0 grams of ethanoic acid and adds the acid catalyst. When the mixture reaches equilibrium, 0.030 moles of ethanoic acid remains. Calculate Kc for this equilibrium. The first thing to do with this question is highlight the key piece of information. So that's the mass of methanol and the mass of ethanoic acid, that the equilibrium moles of ethanoic acid is 0.03 moles, and that we want to calculate Kc for this equilibrium. So the first equation triangle we're going to use is one where we've got mass at the top, and mass is equal to moles times the relative formula mass. So we're going to calculate the moles here, where we've got 9.6, we're going to divide by 12 plus 3 plus 16 plus 1, which is the relative formula mass of methanol, and that equals 32, and it's going to equal 0.3 moles when you divide. Then we're going to work out the moles of ethanoic acid, which is 12 divided by 12 plus 3 plus 12 plus 16 times 2 plus 1. So when we divide this, we get 0.2 moles. So then we're going to do what's called an ice equation, where you have each of your species and then you have the initial moles, change in moles, and equilibrium moles. So if we start by writing out our species, we have CH3OH, we have CH3COOH, we have CH3COOCH3, and we have water. So this is a standard esterification, where you've got an alcohol and a carboxylic acid producing an ester and water. So next we're going to look at their initial moles, their change in moles and their equilibrium moles. So initially methanol is going to have 0.3 moles and ethanoic acid has 0.2, whereas our products of the equilibrium will start with 0. So we're told that the reaction mixture reaches equilibrium and we have 0.03 moles of ethanoic acid, so we can write this in our table, 0.03. So that's a change in moles of minus 0.17. So that's going to be the same because it's the same molar ratio, but where we have our products, we're going to add 0.17 rather than subtracting. So we have 0.17 of our ester, 0.17 of our water, and we have 0.13 moles of our methanol left. Then we write an expression for Kc. So Kc is equal to the concentration of our ester, so CH3COOCH3, multiplied by the concentration of water, divided by the concentration of methanol, then multiplied by the concentration of ethanoic acid, so CH3COOH. So we don't have the volume, But that doesn't matter because the volumes will cancel out. So if we write this expression for Kc and use volume as V, we would have 0.17 divided by V in square brackets multiplied by 0.17 divided by V in square brackets divided by 0.13 divided by V in square brackets times by 0.03 divided by V. So all the volumes here are going to cancel out. So it doesn't matter that we haven't got a volume to work out concentration. So if we ignore volume and we just type in the numbers in this expression, we get 7.4 as our value for Kc, which we can write on the answer line provided. To get the 4 marks for this question, you get a mark for working out initial moles, you get 2 marks for working out equilibrium moles, and then you get 1 mark for using your Kc expression to work out Kc. This question is about halogens. Part A. A student adds a solution of bromine in an organic solvent to 2 test tubes. The student adds aqueous sodium chloride to one test tube and aqueous sodium iodide to the other test tube. The student shakes the mixtures, allows them to settle, and records the colour of the organic layer in each mixture. Explain how the student's results provide evidence for the trend in reactivity of the halogens, down group 17 or 7. And write an ionic equation for any reaction that takes place. Use your chemical knowledge to explain the trend in reactivity. So reactivity decreases down the group, which means that bromine is less reactive than chlorine. So the orange organic layer is going to contain bromine that doesn't react, and then the violet organic layer, because iodine is less reactive than bromine, so that's going to displace, and the violet is going to contain iodine. So that's the first point we need to write for this question. So now let's write the ionic equation. So the ionic equation is going to be with the violet one because the orange one, there's no reaction, so we can't really do an equation because it will just be the same on both sides. So if we look at sodium iodide, so we've got iodine ions, so iodide ions, and we're reacting with bromine. So because bromine is more reactive than iodine, we're going to produce these bromide ions and then iodine. So we need to balance the equation by putting a 2 here and then 2 in front of the bromide ions. So this is our ionic equation. Now we need to move on to the reasoning using chemical knowledge. So with this chemical reasoning or chemical knowledge, we're going to talk about the trend going down the group or down group 7. So the first bullet point we're going to write is that the reactivity is going to decrease. The second bullet point is that the oxidizing power is going to decrease, which we can see in this ionic equation because iodine, which is lower in group 7, is not oxidizing bromine, it's reducing it, so its oxidizing power is decreasing. Also, there's a greater atomic radius as you go down the group, and that's going to mean that there's going to be less nuclear attraction as you go down the group because of this bigger atomic radius. To get the 5 marks for this question, you get a mark for saying that the orange organic layer contains bromine and there's no reaction, and violet contains iodine. You get your 2nd mark for your ionic equation. You get your 3rd mark for saying that down the group the reactivity decreases, and then one of 4 statements. So the oxidizing power decreases, you gain electrons less easily, you form a negative ion less easily, less energy is released when electrons are gained. Then you get your 4th mark for saying that there is a greater atomic radius, or more shells or more shielding, one of those 3. And then you get your 5th mark for saying that there's less nuclear attraction down the group. Part B. Chlorine is used in water treatment. State 1 benefit and 1 risk of using chlorine in water treatment. So let's start with a benefit of chlorine. So the benefit is that it's going to kill bacteria. But the risk is it's toxic or poisonous. So this is one risk. There are two more risks you could write for this question. So the other risks are that you form chlorinated hydrocarbons or you form carcinogens or toxic compounds. To get the mark for this question, you must have a correct risk and benefit. So the only correct benefit that they'll accept in this question is that it kills bacteria. Part C. Compound A contains bromine and fluorine only and has a boiling point of 41 degrees Celsius. 1.26 grams of compound A is heated to 80 degrees Celsius. The volume of gas produced is 0.209 decimeters cubed. Under the conditions used, 1 mole of gas molecules has a volume of 29.0 decimeters cubed. Determine the molecular formula of compound A. So firstly with this question we need to highlight the key pieces of information. So that's that we have bromine and fluorine only, we have 1.26 grams of compound A, we have a volume of gas produced at 0.209 decimeters cubed, and that 1 mole of gas is equal to 29 decimeters cubed. We want to work out the molecular formula. So firstly we're going to do 0.209 divided by 29. So that's similar to when you have that 1 mole of gas equals 24 decimeters cubed. You divide your volume of gas by 24 and then you get moles. So if we do this but with 29, we get 0.00721 moles of A. So then we're going to use an equation triangle. So the equation triangle that we're going to use is mass is equal to moles times the relative formula mass. So if we work out the relative formula mass, that's going to be 1.26, which is our mass of A, divided by 0.00721 moles, which equals 174.8, which is the relative formula mass of A. Now we're told we have bromine and fluorine only. Bromine has the relative atomic mass of 79.9 and fluorine has a relative atomic mass of 19. So if we start by subtracting the bigger relative atomic mass, which is 79.9, if we minus 79.9, we get 94.9. If we minused 79.9 again, we would get 15. And 15 is too small, it's lower than 19, so it can't be that because we're told it has bromine and fluorine. So we know it's got 1 bromine because you can only minus 1 bromine. And then if we divide by 19, we get 5. So that means we've got 5 fluorines. So it's going to be BrF5 as its molecular formula. To get the 3 marks for this question, you get a mark for working out the moles of A, a mark for working out the relative formula mass of A, and a mark for working out the molecular formula of BrF5. Part A. B and C are compounds of 2 different transition elements. A student carries out test tube reactions on aqueous solutions of B and C. The observations of the student's tests are shown below. Analyse the results to identify B to H and construct ionic equations for the formation of products D to H. So let's start with looking at B. So B is FeSO4 or iron sulfate. And that's because if we look at test 1, we've got a green precipitate called D. And that's when you add ammonia dropwise. So doing this and getting a green precipitate, that is a test for iron 2+. So we can write that test 1 is showing that iron 2+ ions are present. Then if we look at test 2, we have a white precipitate G. So this white precipitate, when we're reacting nitric acid followed by barium nitrate, that's a test for the sulfate ions that we have in B. So we can say that test 2 shows that SO4 2- ions are present. Then we can start thinking about what precipitate D and G are. So if we do D first, D is equal to FeOH2, or iron hydroxide, and G is equal to barium sulfate. So D is because we're adding this base, we're adding OH minus to iron 2+, so we get the compound D as a precipitate. And then G is because we've got this sulfate ion, it likes to be with barium, so it's going to displace this nitrate ion. So this we've looked at B because we've got no change with test 3. Now if we look at C, so C is equal to chromium chlorine 3, or chromium chloride. So the way we can work this out is if we look at test 1, we have a grey-green precipitate E and then a purple solution F. So these colour changes when you react with a little bit of ammonia and then a lot of ammonia. So that is a test for chromium 3+ ions. So they're present because we've got positive test. And then if we look at test 3, because test 2 has no change, in test 3 we have a white precipitate H. And that's when we are adding this silver nitrate to nitric acid. We're getting this white precipitate. And that's a test for a halogen. And because we've got a white precipitate, we know it's going to be chlorine, or a chloride ion that's present. So that's how we can work out what C is. Then we need to look at E, F, and H. So looking at E first, similar to looking at B, we have CrOH3. So rather than 2 in ion, because in iron we've got this 2+ charge, so we need 2 OH minuses. In chromium we have this 3+ charge, so we need 3 OH minuses to balance this. Then if we look at F, that's going to be square brackets CrNH3, and we need 6 of these, and then we're going to get a 3+ charge. And that's because we've got this excess of ammonia, so it's present in our complex. And then finally, H, we have silver chloride. So that's a common test for halogens. Now we need to construct these ionic equations. So if we start looking at D, so that's going to be iron 2+ plus OH minus going to FeOH2. So we need 2 OH minuses. So, and then if we go on to E, it's a pretty similar equation where we have Cr3+ plus 3 OH minus, and that produces CrOH3. So these are our 2 hydroxides, and they're very similar ionic equations. Finally, if we look at F, so we're starting with our product from the last step. So we're starting with E, and then we're adding more ammonia. So starting with E, we start with CrOH3. Then we're going to add ammonia because we're adding excess ammonia. And then we're going to produce this complex of CrNH3 6 3+ plus 3 OH minus, because this ligand has been substituted for the NH3 or ammonia ligand. Then if we look at G, that's going to be Ba2+ plus SO4 2-, and then that's going to produce BaSO4. So here the arrow's slightly slanted, but it's producing barium sulfate. And that's because we've got this 2+ charge present in the barium nitrate, and then you're replacing the nitrate ion with the sulfate ion. And finally, if we look at the formation of H, so that's going to be a silver ion plus a chloride ion producing silver chloride of AgCl. So to get the 6 marks for this question, it's a level response question, which means there aren't specific marking points. Instead, you must have all 3 tests covered in detail, with at least 6 of B to H identified correctly, and the equations must be mostly correct. You must also have a well-defined line of reasoning which is clear and logically structured, which we have in this question, with showing what's present in each test. We have the ionic equations for all of the relevant reactions, and then we've correctly identified B to G. Part B. A compound of nickel J has the formula NH4(2)NiSCnX(NH3y) and contains SCN- and NH3 ligands. The percentage by mass of 3 of the elements in compound J is shown below. Ni is 16.26%, S is 35.56%, N is 31.00%. Part 1. Calculate the values of X and Y in the formula of compound J. Let's start by highlighting the key pieces of information in this question. So that would be the formula of J and the percentage by masses of the 3 elements, and that we need to find the values of X and Y. So looking at the percentage by masses, we can work out the ratio of nickel to sulfur to nitrogen. So what we need to do is 16.26, so the percentage, divided by the relative atomic mass, which would be 58.7 for nickel. Then we do the same for sulfur, so that's 35.56 divided by 32.1 for sulfur. And then for nitrogen, we have 31.00 divided by 14. So this equals 0.277 to 1.1 to 2.21. So then we divide by the smallest, so 0.277 divide by 0.277 and divide by 0.277. So this equals 1 to 4 to 8 as the ratio of nickel to sulfur to nitrogen. So then we know that X is going to be equal to 4 because the only place we have sulfur is where X is, and there are 4 sulfurs, so X must be 4. But then for Y, we know that we've got 2 nitrogens in this NH2 here, or NH4 brackets 2. So there's 2 nitrogens here. There's however much X's nitrogens, and then you've got Y here. So, and all of these added together will equal 8. So 2 plus X plus Y is equal to 8. Well, we know that X is 4, so that's going to be 2 plus 4 plus Y is equal to 8. So Y must be 2, because 2 plus 4 is 6 and 8 minus 6 is 2. To get the 3 marks for this question, you get a mark for your ratio, so 1 to 4 to 8. Then you get a mark for X and a mark for Y. Part 2. Determine the oxidation number of nickel in compound J. So for this question, we're looking at the formula and trying to work out the oxidation number of compound J. So this could also be known as the charge of nickel in compound J. So we know that the only ligand with a charge is this SCN-, and we know that X is 4 from the previous question. So we have a 4- charge for all of our ligands because ammonia, or NH3, has a 0 charge. Then we need to look at this NH4. So this is what most people don't look at. This will have a charge of +1, and there are 2 of them, so that's +2. So if we did -4 and then +2, that's going to be -2, but we want a 0 overall charge. So that means that the oxidation number of nickel must be plus 2 in order to make this 0, because minus 2 plus 2 is equal to 0. And to get the mark for this question, you must write plus 2. Part C. Sodium sulfite 4, Na2SO3, is used as a preservative in some foods. Food safety legislation allows a maximum of 850 milligrams of Na2SO3 per kilogram of burger meat. A chemist determines the amount of Na2SO3 in a sample of burger meat using a manganate 7 titration. Step 1. The Na2SO3 from 525 grams of burger meat is extracted to form a solution containing SO3 2- aqueous ions. Step 2. The solution from step 1 is made up to 250 centimeters cubed in a volumetric flask with water. 25 centimeters cubed of this diluted solution is pipetted into a conical flask. Step 3. The pipetted solution from step 2 is acidified with dilute sulfuric acid and then titrated with 0.01 moles per decimeter cubed potassium manganate 7, KMnO4. 12.60 centimeters cubed of KMnO4 aqueous is required to reach the end point. Analyze the results to determine whether the burger meat complies with food safety legislation. Firstly, with this question, let's highlight the key pieces of information. So that's going to be the mass of burger meat we're using, the volumes in the titration, so the scale factor of 10, the concentration of potassium manganate or KMnO4, the volume required to reach the end point, and then we're going to start using some equations. So the first equation we're going to use is an equation triangle of the number of moles is equal to the volume times concentration. So we can work out the moles of the manganate ions. So we can do 0.01, which is its concentration, multiplied by 12.6 times 10 to the negative 3, because we're converting centimeters cubed into decimeters cubed. And that equals 1.26 times 10 to the negative 4 moles of MnO4 minus. Then if we look at the scale factor of the manganate and the sulfate ions, we have a 2:5 ratio. So to get the moles of sulfate ions, we need to do 1.26 times 10 to the negative 4, then divide by 2 and times by 5, which equals 3.15 times 10 to the negative 4 moles of the sulfate ions, so SO3 2- in 25 centimeters cubed. This is very important because we need to use the scale factor of 10 to get to 250 centimeters cubed. So we do 3.15 times 10 to the negative 4 multiplied by 10, and we get 3.15 times 10 to the negative 3 moles of SO3 2- in 250 centimeters cubed. So now we've effectively used the molar ratio and the scale factor to get the moles of the sulfate ions. Now we're going to use a second equation triangle to help us work out mass. So mass is equal to moles times relative formula mass. So we've already got the moles, which is 3.15 times 10 to the negative 3. And then we want to multiply by the relative formula mass of this sodium sulfite, so Na2SO3. So that's going to be 23 times 2, which is the relative atomic mass of sodium, then plus 32.1, which is the relative atomic mass of sulfur, plus 3 times 16, which is the relative atomic mass of oxygen. And then if we do this, we get 0.397 grams of sodium sulfate, so Na2SO3, in 525 grams of meat. but we want it per kilogram, which is right at the beginning of the question. So if we're trying to convert this into per kilogram, we need to do 0.397 multiplied by 1,000 divided by 525 grams. So 1,000 grams is in a kilogram, and we're dividing by our number of grams. So this equals 0.756.6 grams, which if we convert to milligrams is 756.6 milligrams. Then we need to look at what we're allowed. So we're allowed 850 milligrams. So 756.6 milligrams is less than 850 milligrams, and therefore our burger meat is complying with these food safety legislation and it's safe to eat from what they've told us. To get the 5 marks for this question, you get a mark for working out the moles of the manganate ions. You get a mark for working out the moles of the sulfate ions. You get a mark for working out how much is in 250 centimeters cubed. Then you get a mark for working out the mass of sodium sulfite in 525 grams. And then you get a mark for working out how much is in a kilogram, and then saying at the end that it's less than 850 milligrams.